Okay. Wait. Hello, hello. Oh, hello. Okay, let's get started. So, any question from this time? We are this window. Okay. This time we finish the global lower bound this time, and this time we started to theorize global search more, and we say is computing this OR function, and we start to talk about applications of this global search algorithm. We know it's an OR function, so wait, where is it? Yeah, we know it's all the global algorithm is solving the OR function, and then we think that end function is very similar to OR function. So you can also use the global algorithm to solve the end function in order square root n query and time. But there are functions like parity where you have no quantum speedup. So now we have so now the big question in quantum computation theory is what is the quantum query complexity of all sorts of problems. And okay, so this is a baby course for quantum query complexity. And the first function we see is this end of ORs, sorry, OR of ends. So yeah, we know OR takes square root n10 and n takes square root 10 n10. And what if we compose the OR function and the n function together? So we think about input once again is a big and big string, and we think it's kind of like a block. So square root n times square root n block. So you will have end of the first row and end of the second row. So you are computing the function where you need to compute the end of every row first, then you compute the OR of all the result from the rows. Okay. So this is once again a function on big N inputs. And if you translate this into English, then it's asking whether there is a row with every element being 1. So that means when you end over every element in this row, you will get 1 as the output. And if you get 1 here, when you over all the row result here, then you will get a 1. Okay. And the other way to visualize this is as a tree. So you have a OR at the top, at the root of your tree, and you have square root n children. And so those children nodes, you need to compute the end here, and each of the end also have a square root n children. So this is like the first row and the second row, etc. And wait, and oh, okay, first row, second row, etc. And what's the query complexity of this OR of n function? And classically, it's pretty easy to see that you need omega n queries. So let's skip that. And quantally, so first we give a dumb algorithm where you just run Grover's algorithm separately. So you run Grover's algorithm for every row. So every row has square root n items. And so if you want to run Grover algorithm, you need square root of square root n, that's n to the 1/4. But you also need a log n factor because you want the error to be very small. You want error to be less than 1 over n. And okay, so each row need n to the 1/4. So every of these need n to the 1/4. And there are square root n rows, so you just times that number with square root n. And total query complexity is n to the 3/4 and times the log n. Okay, so that's one way to get a quantum speedup. But you think, is there a way to do better? And there is. So you can also do the second step with global search. And the idea is that so the first part of algorithm here, this is a quantum algorithm, right? So you can think this quantum algorithm as an oracle. So obviously it will have a different output form, but you can easily do phase kickback and things to turn this quantum algorithm into this form that is form of the oracle we need in our Gover's algorithm. So you can turn this quantum algorithm into like a sub-algorithm or oracle such that you can input index for a row. So you want to query ith row, and then you will spend these n to the 1/4 queries, and so these all require n to the 1/4 queries, and you will compute the end of all items in that row. Okay. And then you do phase kickback to make it phase version. So you actually, when you do apply this oracle, it becomes -1 to the end of the result. Okay. And so if you have this oracle, then you can run another Grover search on this oracle, right? Now you are Grover search over this I. Okay. So we can run this Grover search recursively, and then you run Grover search on this I, and now this I has square root items, and so you need to run the outer Grover another square root of square root n time. And so the total number of query you need, so you need to run the outer Grover this n to the 1/4 time, and each query of the outer loop is doing the inner loop, and the inner loop is this all, and each of these is actually n to the 1/4. So we need to times another n to the 1/4, and this log n. So the total number of query is this square root n times another log factor. And this is kind of expect, because we think about you are doing Grover search on an item, and kind of Grover search on an item, and then you only need square root n queries. So that's pretty cool. And okay, so that's for last time, right? That's the end of review. I guess before we go to new content, any question? Otherwise, okay. So let's go to the more complicated function. So end of tree. And the idea is we are generalizing this, right? So we think about this OR of end is like a two-level tree. The top of is OR, and the second layer is end. But what about we put this tree on many levels? So you have OR and some fan out, maybe constant, maybe more, but whatever. Some OR and fan out to end, and fan out to OR, and fan out to end. So you just have this alternating layers of OR and end. And the tree depth now is arbitrary. So before we just have this two-level tree, and now we want to generalize this to arbitrary level tree. And yeah, we want to compute this function. And we want to see what's this query complexity. And before we talk about query complexity, let's motivate this a little bit. So this is actually a very practical question, because this OR and tree, computing this can be used to decide any games. So the games is actually, any turn-based game. So for like chess or Go. So this is 西洋棋, and 围棋. Okay, and why is this true? It's because we are computing we are computing a game state here. So basically what we are computing is, at this node, can I win or I already lose if everyone play perfectly. So if the value of a node is 1, that means if the game state is that means that game state I will win. And if the value is 0, means I will lose. And so why is that? Because all are the turn, so it's two-player game, so there is me and my opponent. So the ORs are my turn, right? So the ORs are my turn. Hey, why is this not working? Excuse me. Excuse me, let me try to fix this. Maybe change one. Okay. Yeah. So the ORs are my turn. And so me. And the and opponent. So that's a U. Okay. So it's two pair again. And so what are we doing OR on my output? Because we are kind of looking at this bottom up, right? So at the end of this tree, there will be some state that maybe I already checked U, so I win, right? So at the start of my turn, and there are many decisions, maybe even more layers. But if there is some state that I already win here, right? So there is one state that I win, then I can, then all those branches are the possible move I can make. Then I can just pick this branch and I will get the win result. Okay? So to determine the gain state at this node, there just be one node that I win. Then I can pick that node to be the move I make and I will win. And similarly, on the opponent turn, right? The opponent will pick whatever base for him that is making me lose. So if there is whatever result that make me lose, then the opponent will pick this branch and I will lose. Okay? So you can see the end tree actually calculating the gain state, where at this state is whether I win or the opponent win. And you can kind of bottom up this and also look at the total end state and calculate all this bottom up and to determine whether this gain is win or loss. And obviously, when you are actually doing this on actual gain, the tree is very long, and there are annoying detail where like the depth can be infinite because the gain is not converging or the gain can actually draw. But ignoring this, so on a high level, any two-player turn-based gain can be written as this end-over tree. So it is very general and useful. And to describe those kind of gain in more detail is called two-player and turn-based. And also zero-sum gain. Zero-sum means that one of us win and one of us lose. Actually, so this is a bit more restricted than zero-sum, but whatever. Yeah, so I should probably not say zero-sum because it means something else. But anyway, so you can see this is a two-player game because it's in turn-based, so you are alternating between my turn and your turn. And anyway, so that's the motivation for this end-over tree. It's very critical function to calculate. And what's the quantum query complexity of this? Now remember, we are still talking about quantum algorithm. And so the first intuition you get is you can run something like this, right? So you run recursive go over. So you just recursive go over each layer up, and and so if you think about recursive go over, and then you think the total number of all possible end configuration is like a big N, and you think you recursive go over up, then that should give you square root and quantum algorithm. But that actually doesn't work, and we will not describe this in detail. But the idea is that the problem comes from this log n factor. Right? So remember, Grover algorithms are not perfect. You always come with some error. So the error at the lowest level of this tree will build up all the way to the top. So if you want your top result to have good error probability, so just like here we say we want the top level order to have high good success probability, then the error here needs to be like 1 over square root n, right? And so here is similar. So here, let's say you have those three things, then you want every one of them to have error probability less than 1 over 3 times some large constant. Then this one you also need to have and then this one you need to have even smaller error probability because there are two. So you need to have like 1 over 3 times 1 over 2, etc. So the error probability, so the precision you need to build up through the depths very fast. And so if you just run recursive Grover, and you check out everything carefully, the precision requirement will eat out all the quantum speedup you get. So you don't get quantum speedup if the depth of the tree is high enough. Okay, so that's really annoying, and but it's still possible to do a very Grover-like algorithm, quantum algorithm, to solve this end-of tree with order square root and query, and I believe also time. But we will not describe this in detail. I will just give you a keyword here, and the keyword is called quantum walk. It's like a generalization of classical randomized walk, but yeah. It's like a quantum version of a classical work, although this work is the result that work on this end tree is a bit weird. And anyway, this is a really cool result. You can get this order square root and quantum algorithm through quantum walk. It will determine whether your end tree result is 0 or 1. Okay, 0 or 1. Yeah. 0 or 1. And that works for any depth and I believe any structure of the tree. So you don't even need to be balanced or what. Okay, really cool. And if you want to see a detail, here is the paper by Fahy, which is my grade school advisor, Edward Fahy, and Goldstone, which is a very famous physicist. I believe he is a Nobel Prize winner. And Sam Gassman, who is Eddie's friend. And anyway, the keyword is NAND tree. So NAND is not AND because I believe if you put a NOT on some of those labels, then a NAND tree is same as an AND OR tree. And the most important information to find the paper is here. This is the archive number. If you want to find the paper, you can look at this up, and it's actually pretty easy, except that it requires some continuous time quantum mechanics, so which we skip for the class. So hopefully it's not too hard. Anyway, that's the end of tree, and it's a very interesting result. Question? Not? Then let's talk about more computer science result, because so this is continuous time quantum walk. Is kind of like sending a wave packet in some physical setting. Anyway, Now let's go to a totally computer science problem, collision problem. And we already see this problem when we run Simon's algorithm. But anyway, the problem setting is this. So it's a query problem. We are given black box access to this function. But now it's not a binary function. It's an end-to-end function. Okay? That's because this is more natural for collision. So we have a function, small f, that okay. So the small f that map from 0 to some big N to 1 to some big N to another to also 1 to big N, and we say N is even to make things easier, and we have a promise on this function. So the small f is either a 1-to-1 function or a 2-to-1 function. Okay. So either every element map to a different element, or every two element will map to the same element, and only half of those elements got mapped by something. So, for example, 1-to-1 function is you map f1 equal to 1 and f2 equal to 2, f3 equal to 3, f4 equal to 4. So if you write out the truth table of f, so the truth table we always like to write is 1, 2, 3, 4. And but if you have a 2-to-1 function, then maybe f1 equal to 1, so maybe the truth table will be 1, 2, 1, 2. Then you see that you have a collision here and a collision here, right? So should be pretty clear what they mean by a collision. Means two output of f being the same. So two different inputs giving same output on this f. So this is f1 equal to f3. Okay, so that's collision. Oh, sorry, that's only the setup of the collision. But now it's pretty clear what we want to do. So the problem is just we have a query access to our small f. Then we want to decide whether it's actually 1-to-1 or 2-to-1. So is there any collision? Okay.
Why N?
Huh?
N, could N is all the number of no problem.
Once again, it's truth table. Okay, so we can say, so I guess classically then it's just like this, right? So classically you can just compute what is f1 and what is f3, etc. And yeah, and you are trying to decide whether there is totally different or there are some collision. Yeah, so that's a problem. And classically, we already see this in, I think I let you do this in homework. But classically, we already see this when we talk about Simon's problem. And so as a review, the query complexity is order square root n, or big theta square root n. So the upper bound is by this birthday attack. The idea is that if you pick two numbers, just pick two random locations. Right? So then you say fix whatever this, then what's the probability that this thing equal to that thing? And well, then that's about probability 1 over n, right? Because everything has a collision. And so there are totally n things, and so the probability that this happen to be a collision of this thing, then that's probability 1 over n. So any random pair being a collision, the probability is 1 over n. And if you pick order square root n items, then so you pick those square root n items, then the number of pair inside is actually what was it? Anyway, is square root n choose 2, and it's about order n. Okay? And so you pick order square root n items, then you will actually see order n pairs between them. And each pair has a probability about 1 over n to be a collision. So you will have like a constant probability to see a collision. Yeah, I should scroll down first. And then you can do this more carefully to calculate the probability and get this constant to be 2 over 3. Okay, do some amplification and stuff. So that's the upper bound, and I believe you already do in your homework that you have a matching lower bound. So that's the classical Curie complexity for collision. And what about quantum Curie complexity for collision? Well, we will see this in many algorithms. So first is a very dumb algorithm. So quantum algorithm 1. You start with querying F1. So you see what is F1. Okay. And this requires one query, which means nothing asymptotic. Then because we know everything has a collision with it, right? Then this F1 also has a collision. So you just global search all the remaining items to see what is x, such that f of x equal to f1. Okay? Yeah. And what's the query complexity of this? The query complexity is 1 plus the square root and query here to find this x. Okay? And well, then that's order square root then. Okay, that's a quantum algorithm, but it's a little bad because there is no quantum speed up. Because we know classically we already have this order square root n algorithm. By yeah, classically we already have this algorithm just by this birthday attack. So if we want a quantum speed up in this question, then we need to kind of do things similar to this birthday attack, right? Was only when we search over things, we only want to see many pairs. Okay, so the quantum algorithm that actually get a speed up is smarter. Okay. So the algorithm we will actually do is so this is only query efficient, but we can make it time efficient. But anyway, so we start with we pick more things. So in the algorithm 1, we only pick one thing, and that's bad. So algorithm 2, we start with looking over many items. Okay? So we pick a random set that has this many items, so order n to the 1/3. Okay? And we just look through all of them. Okay? So we have those F1, F2. Let's say if we pick just the first n over 3. Although we want to randomize, so it works for worst case. That's F1, F2, F1 over 1 over 3. So we just query them and we write down all the results. And then we random select another n to the 2/3 items. Okay? But very importantly, we don't query this set here yet. Because we know classically we only need n to the 1/2 queries to finish everything, right? So if we look at everything inside is n to the 2/3, that's already more than classical query complexity. So that's bad, but we can decide some set that we want to look over. Okay. And now the interesting part. Now we global search through everything in S2. So we have a picture here. We have S1 that we know everything. Right? We know every element in this S1. Then there is a S2 that we want to compare to S1. So obviously, if you see a collision in S1, you just output that you see a collision. But I guess we don't need that anyway. Because that's low probability anyway. Because number of pairs here is only n to the 2/3, and you know the collision probability is 1/n, so very low probability you see a collision here. Anyway, so we have this n to the 1/3 size S1, and we have this bigger S2 that has n to the 2/3 items. And what we go over search over is everything inside S2, and we want to see where this item is a collision with any item in S1. Okay, so this is a key step. And yeah. So in other words, we say item Y in S2 is marked. So this is the one we are talking about. Talking this in terms of go over search. So we are thinking we are go over search over the items in S2, and the mark item is the item such that there is some x inside x1 such that f of x equal to f y. Why am I? Oh, I just writing this very ugly. So f of x equal to f of y. Okay. And this is what we do. And but now you think this is very efficient, right? Because for everyone you need to compare many items inside S1. There are n to the 1/3 items. But now there is a cool thing about query complexity is that we already queried everything in S1. So to do this comparison, you don't need many queries. You only need to query f of y, because those you already know and you write down classically. So you can just set up a classical algorithm that is you input whatever f of y and you will compare through all of those, and you don't require any extra query to do the comparison. So this checking mark item step actually only require one query. Okay, only one query. So this is a key step here. You only need one query to check an item in S2, such that f of y is different from every f of x inside S1. Okay, and then that works. So the total number of query, we balance all things nicely. The total number of query we need is n to a 1/3 query that you need to construct the information about everything in S1. And this go over search through S2 is square root. There are n to a 2/3 item here. Then you take a square root, so that's n to 1/3. And so n to 1/3 plus n to 1/3 is still order 1 n to 1/3 queries. Okay. And okay, so the number of query we need is pretty good. It's less than classical. But do we find do we find a collision with high probability? And that's yes, because the number of pairs we have checked now is n to the 1/3 times n to the 2/3, right? Because pairs. So n to 1/3 here, n to a 2/3 here. So number of pairs is multiplying together. So number of pairs we search through is order n, and so we can run an argument similar to the birthday attack, saying that we have seen through order n pairs, and each pair has 1/n probability being a collision. So we have a constant probability of seeing a collision. Okay. Okay, so that's the query complexity. And actually, you can also do this in order n to the 1/3 time complexity. That is, you just need to do this part smarter, right? Saying this by, we say we do this. You can do this dumb way, you write down everything, and every time there is a y inside, you just compare through your huge list of n over n to 1/3 items. But there are data structures that let you do this much faster. So there are data structures such that you can construct it, and there are lots of items, so there are n to 1/3 items. And but you can compare through all items, so you can input some f of y inside and compare where it's different from everything with just, I believe, log n time. Okay, so that's possible to do with basically just classical data structure. Okay. Although you need some requirement. Okay. But it's possible with a smart data structure, and that will give you an order n to 1/3 time quantum algorithm to solve collision problem. And this interesting problem, this algorithm we talk about is actually optimal. So, but the lower bound is quite complicated, so we just state the results that there is a matching lower bound, omega 1 to 1/3. So once again, if you want to look up the result, here is the result give you this omega n to 1/3. It's by Andrews and Banis, and here is the archive number. And it actually uses a different lower bound technique than what we talk about in Goblet algorithm. It's called polynomial method. It's quite interesting. It tracks the success probability of your quantum algorithm as a polynomial, and says that if the number of query, so number of quantum query you use will be about the degree of your polynomial. Okay? Or so the degree of your polynomial, I would say, is upper bounded by the number of query you use in your quantum algorithm polynomial. And so you just need to prove that your polynomial has a very high degree. Then it means that you need lots of quantum query to make such a weird polynomial. So that's pretty interesting, although we don't quite have time to cover it in this class. So yeah, and also the way we do to prove our global lower bound like this is called, so like the tracking progress is called, where are we? It's me. Yeah. So the way we did is called the adversary method. Okay. Okay. So those are pretty different way to lower bound quantum query complexity. And yeah. Anyway, so this paper, you can look it up to see this omega n to 1/3 lower bound. And there are also earlier paper that also give omega n to 1/3 lower bound, but it has a slightly different setting. So we have been saying that our collision problem. Wait, where are we? Okay, here. Well, collision problem, our function is from 1 to n to 1 to n. But for lower bound, we need to relax our function to something bigger. So it will be 1 to n to some 1 to n. and I think your m need to be like n squared or something like this, some polynomial of n. So the earlier work is that you have a big m, then you have this n to a 1/3 lower bound. But anyway, this Ambani's paper, yeah, that Ambani's paper give you a bound for m equal to n, so that's nice. Yeah. So the larger range means bigger n. Any question? If not, then let's talk about an even harder problem. So I guess the problem statement is easier than collision. So this is very similar to collision, except that there is no promise. So we also have our f from 1 to n to 1 to n. Okay. And just as you see, so sometimes people do like 1 to n for the easier lower bound, but for simplicity, we just think the range and the domain is the same. And anyway, so the function is 1 to n to 1 to n, but now the function is no promise. The function can be anything. And now we just want to decide whether f is 1 to 1 or there is any collision at all. But you see that, so we want to decide whether f is 1 to 1 or there is a collision of f, because range is totally the same if it's not 1 to 1. Sorry. Anyway, yeah, it's 1 to 1 or there is a collision. And you can feel that this problem is harder because there was a lot of collision before, right? So for the collision problem, you know that every element must be have a collision with another element. But now, and we say that the number of collision pair is order n, right? Because there are totally n over 2 collisions. But for element instances, there is no promise on this function, so number collision can be just 1. So, for example, your function can be this. Let's write this longer. So your function can be as 1, 2, 3, and n minus 1 and 2, and so you only have 1 collision out of your whole n squared pairs. So it's much harder to find this collision because the number of collision can be much smaller. So we expect both the quantum and the classical query complexity to be larger. Okay. And yeah, anyway, here's the example. And easy example, f choose table 1, 2, 3, 1, and this 1 and 1 is a collision. So classically, there is no smart algorithm at all, and you just need to look over every item to find out the collision. And I think it's not surprising, right? So because even if you look through all the n-1 items, and they are all different, and the last item can be collision to anything else. So yeah, it has a lower bound of n, and the upper bound of n is trivially you just look through everything. Okay. And quantumly there is still a speed up, but let's first talk about not totally optimal quantum algorithm, but it's very similar to a collision algorithm. Actually, we have 5 minutes. Maybe we will have. Can we talk about this in 5 minutes? Okay, let's try to do this. Yeah. So we'll review this in next class. So quantally, we first talk about this not optimal algorithm, and you only need order n to a 3/4 queries, And it's very similar to the collision algorithm, so we do kind of, well, it's more complicated because we do recursive Gover. But anyway, so there are totally n items, and first we randomly chop up those n items into square root n blocks, and each block have square root n items. So this is just picking square root n item, and say is the first block, and say another is the second block, etc. So nothing really happened. Okay. And we have not query anything, we are just deciding that some of the item is the first block and some of the item is the second block, etc. And they are totally square root n blocks. Okay. And now we'll run Grover recursively. So first there is this inner loop of Grover, and you will run on, it can be run on any block. Let's say we run on block I, okay? And so it's not really pick on one block, so it's on block I. So on block I. On block I, we query all element in it, okay? And we also check whether there is a collision inside that require no more queries because we query everything. Okay? So this block SI, we can query everything inside and we know everything. Okay? And then we can run the collision finding algorithm just like before. But now we don't have another S2. Okay? So we just look through everything else because now we have more query to spend. Now we just look through everything else and compare to all the non-resolved in SI. Yeah? Just like we do in collision. Remember collision, we have this S1, S2. And we look through everything S2 to see does it has a collision to anything inside S1. Now it's similar, we see everything. I guess we can also look inside S1. So we look through everything and see do they have a collision to anything inside S1. Okay. So now the S2 is everything. And well, so that's an inner loop too. So if there is a pair where one element is in S1 and one element is whatever place, so then this inner loop will find it. Sorry, not S1, SI. Okay. So if the collision pair has one element in SI, we'll find it, as we said. And now the number we need here is this probability. And why is it this probability? Well, because the size of SI is square root n, right? So we just think about the first item of your pair of collision, and because we pick SI uniformly random, so the probability that some item is in SI is just square root n over n, so that's 1 over square root n. Okay, so that's easy probability. And what's the query number of query we use? So it's similar to the collision problem before, but with different number. So we need to query everything inside SI, the square root n, and we need to run this global search over everything, and so the square root over everything as n, so square root n. So square root n plus square root n, that's all the square root n. And we have 1 minute. Okay, so that's the inner loop, and the outer loop is then just go over this I. We do outer loop of Grover search through every possible SI. Okay. And yeah, so let's take a break, but you can see a result here. Okay. So yeah, let's take a break. I guess this is not important.这样。作业好。OK。可以，应该也可以，也可以作弊。
设定我应该要怎么分流？就是一个的话，那个设定是用 OS， 然后UK 这样。那如果是多个的话，我们发现这个会变成 O alpha 这边 O beta 这边，beta 就是所有f of x 等于1的这些。
O beta。有N个你就有beta 吗？我不太知道，你要有所有N个马克莱肯的东西吧？我想想看，这是怎么写的？我是说1的0或是N个，对不对？所以应该是0的还是全0嘛？0的还是全0，然后N个的。
就变成 CN 区。
对啊，你就要说你有那个 CN 取 N 个 ，CN 取 N 个，然后所以就是有 N 个 mark，N 个 mark 这样。对，你说贝塔有点奇怪，贝塔是，好像也没有特别奇怪，这样，所以这里的 x 就会变成，就是要说那要那个。要把 x 其实就只要 label 出你这个 CN 是哪一个热的，所以就是 x 就要变成你的那个 m 个 location 的东西。
可以吧？其实我对这个就是怎么设定这个general的这个 algorithm， 为什么是 OX 这个为什么不是其他东西？就是为什么不是可能不是 x 的加起来
？x 的加起来什么意思？我当初写 OX 只是方便而已啊。x 又是 input 吗？
假设一个，是有。那为什么它可以假设说，就是它是用 OX？ 那假设一般的这种content search algorithm就是会用到 OX。
可是这是它的 oracle， 它当然要用啊，不用的话怎么找到 x 是什么？不用的话
假设其他东西，比如说它用什么 O sigma， 不是 x 的加起来之类的。
不行啊，它 oracle 就是固定的东西啊。然后 oracle 是虽然说有，我要让你混乱一下，但是虽然说是有一些证明的时候说，我做到一半把 OX 换成别的东西的，但是我们现在这里定义的是一个非常单纯的东西嘛。我们是说我们的 algorithm 这样跑的时候。algorithm 就会一直跑过来，对吧？它会一直说 UO 这样子，对，UO。我们这只是在 track algorithm state 嘛。那这个 OX 当然就是这 oracle 是你不能变的，因为它是一个 black box 给你嘛。就是你在解的时候，你的 f 是什么，那你这个 OX 其实是 OF 嘛，你对应的 OF 就会是什么？那我们这里说 OX 只是给个名字嘛，因为我们的 f 有一个比较简单的形式。我们说我们有 f sub x 才有这个 f(x) 等于1，然后 f of y 等于0的情况。所以我们这个 OX 是把 对啊 global 的话也是固定的一个 f of x 啊。
它的这个会变，
只是剩下的 f 就有可能很多 possibility 的地方。如果你的 f 没有，因为我们是说我们就只看这些很明微的是1的 f 嘛，但实际上的 f 可能是任意的东西啊。所以我们看这 truth table 的时候，你的这个 f 的 truth table 还有可能01100之类的嘛。那你这里就不能只是个1到 b 个 n 的 x， 你的 x 就你如果要完全写出来的话，那就是要把这整个 b 跟 b string 写出来嘛，对吧？因为你要用，可能就是用我们后面讲法 ，x 你要完全表示这个 f 的话，就是 b 跟 b string 这样，就是这样子。例如说01000之类的东西，如果要写很长的话。我这一题要做 b 的方法可以做就是你可以 reduce 到一般的 global 吧。对吧？但是我记得我之前干过硬做是可以做出来的，忘记是怎样，要努力一点。
这个要实验取验才可以觉得出来。
应该没错吧？的确是实验取验，我不太记得细节，但是记得是做过。
如果是一般就是设定就是 OF，
对啊，你就 OF。
那它对应到的问题是什么？它是我被它，
我想想看它会是什么？不会哦，这个你要想一下。其实也不是的，它要是 projector 对不对？没有，它不会是这样子，它要是这样的东西，你可能 x1 加 x2
那其实就是一个，
对啊，其实就很像，这样写出来就会了，
合起来就是一样，没有，可是
就这里会有 n 个东西吗？因为它就这 n 个东西就要给你负1嘛。
那我还是一样在算那个 dk 的时候。
对啊，就是 dk 那里你要处理一个仔细的。
这里就变 c 干嘛？阿法就会有什么 cn 取 n。
这我看不太清楚的，可能是，我不知道你说的阿法是。对啊，就会有点像那个，对。
可是那个 cn 取 n。
反正就是也加法的数你要数清楚。
我想说，这个有没有办法叫这个叫 dk 范，有没有办法变回原本这只有一个的 dk 这样？跟它扯上关系，然后就
有点困难吧？你要在这里做 reduction， 那你不要扯关系，你不如直接做 reduction。
所以就是要那整个重新整个。
对啊，其实就是。
小于这种确定方式，然后
小于等于，对。
要证明这个。
差不多这样。所以要硬做的话是这样子，就是那个 O 的地方。其实我记得没有太难算吧，难的是那个 notation 要写清楚，就比较烦，因为你有什么 cn 的东西嘛。所以说你代数不要写到自己昏头这样。
那个
语大学好像是作弊吧，我有点忘了。就是你就reduce 到只有一个的东西，是怎样啊？对吧？Hello. Okay. Yeah, let's get back. So our element distinctness algorithm. And okay, let's do a quick review. So our first algorithm one is order n to the 3/4 query algorithm, and to solve element distinctness problem, and it uses this recursive Gover structure. So first we randomly divide, so we should say randomly divide or element into square root n block of size square root n. So just pick square root n item here, square root n item, etc. And so it's a recursive Gover. So we have inner loop and the outer loop. So inner loop is very similar to what we did in the collision problem. So we will so inner loop has some input I, means that we are checking the ith block, and so it will query everything inside this Si, and then then do a Gover search over everything else to see whether there is a collision pair such that one of them is in this other thing, and one of them one of them in this Si. So I can even not say this, and that makes things easier. So Y in N. Okay. So we see everything Si, then we go over through everything to see where there is a pair such that one of them is in Si and one of them is anywhere. And just like in the collision problem, this this Gover only requires square root and query because we already record everything inside this Si. And then we can see the collision probability finding here is 1 with square root n, but not very important. Yeah. And anyway, so the total number of query to run this inner query on some input I is square root n plus square root n. Okay. And so it's order square root n. And now we think this inner loop is some quantum algorithm, so we can feed it to another Gover algorithm. Okay. So we feed it into another Gover algorithm that searches through all possible block I. Okay. And so the total number of block is square root n. So if you want to search through everything, the total number of block is square root n, then you go over it, so that's square root n. And the inner loop only need square root n query. So total number of query is order n to the 3/4. Okay. And so this is not optimal, but you already see a quantum speed up here. So remember, classical is theta n. Okay. So 3/4/n. So that's a win, and it's quite complicated Gover search. So it's kind of like 3 level of Gover, but 2. I guess it's still 2 level. But anyway, it's a quite cool algorithm. Any question?
I'm not sure. Is it inner to compare with the outer, or?
The inner is getting fit to the outer, so it's like an AND/OR tree, right? Remember, it's not AND/OR tree, the OR of AND. Oh, do we have it here? Right? So it's like this algorithm, where you have inner loop that do something, and you feed that, so you think the inner loop as a quantum algorithm. So you feed the result to an outer loop that do Grover search on the inner loop result. Okay. So yeah, so this algorithm combines two ideas we talked about. One is this recursive Grover on oil event, and another is this collision finding algorithm where we query everything inside some set. Then you can compare pairs more efficiently because you already know everything inside this smaller subset. Okay. Yeah. So that's n to the 3/4. And algorithm 2. This is the optimal algorithm. You actually take n to the 2/3 queries. And once again, it's about quantum work, but it's actually a little different quantum work. So just so you are not too confused if you actually look at the paper. So this is discrete time quantum work by Andres and Bennis, and here is the archive number. And so this quantum work is actually like random work. So it's like a quantum version of classical random walk. And okay, so this is a really cool paper. It's quite technical. And for lower bound, so there is a matching lower bound. So omega n to the 2/3. And the lower bound is actually easy now because you can just reduce the lower bound to the collision problem. And yeah, excuse me. Yeah, and you can do that in your homework. So, any question about element distinctness? It's quite a cool subject. And obviously, you can see that collision and element distinctness are quite useful problems to think about because, like, some you can use them to break some crypto system, right? So like sometimes you do a H function, then you want to see whether your H value has a collision, etc. Okay. So all sorts of things for collision and element distinctness. Okay. And another algorithm. Wait, where are we? Okay. Or another problem that have can be put as a subalgorithm everywhere is this minimal finding. And the problem, well, it's very similar to its name. So you are trying to find the minimal of your function. And so more formally, we are still where a function has discrete input, so we are still have input 1 to big N. And now we think the output is some real number, although it's a little weird. Doesn't really matter, it needs to be some set that can be ordered. Okay. So anyway, so you have discrete input 1 to N, and you have function value, that's a real number. And as the title says, we want to find a minimal. So if I want to find some input x, maybe x is here, such that f of x is a minimal. And if you want to write down all the equations, that means that x is such that for y not equal to x, f of x is less equal to f of y. Okay. So you have this kind of oracle, and you want to find the minimal x. And what's the okay? So obviously the classical query complexity is older, and we didn't say it here. I think that's pretty obvious. And the quantum query complexity, once again, there is a quantum speed up, and it's actually as much speed up as Grover's algorithm. You can see that hopefully you can feel this is pretty similar to the Gover's algorithm. You are trying to search for one item, okay? But it's more complicated, and you will and yeah, it's a homework problem to show that you can do this in order square root n10. And this is optimal because you can do a reduction to search to show that you need at least omega square root n10. I think we can just write a reduction here because it's really easy. That just promise your function is that you find the minimal, right? So you just flip your Grover around, so your function is 1, 1, 1, 1, 1, 1, 1, 1, 1. Sorry, the 1 and the block looks very similar now. So let's draw this better. So if you plug, so your f is 1, 1, 1, 1, 1, 1 is, and there's a 0 somewhere, right? Now this is just go over with 0 and 1 flipped, and so you are trying to find the location of 0. That's minimum finding. So if you can do minimum finding, then you can find the location of the 0, and then you can solve the search version of the go over problem. And we know that has omega square root and lower bound. Okay, so that's easy. And yeah, the upper bound is harder, and you can think about how to do it in homework, and it's in some very short paper. So okay. Anyway, any question? I think this is maybe we'll have a little more. Yeah. So these are the applications. So we have 6 different problems that we can solve for by Grover's algorithm. And any question? Otherwise, let's do a little bit of complexity theory. Okay. I think we actually skipped. We talked about P and NP, right? But we didn't talk about any quantum complexity class. So here is some catch up. So, but we need to change our mind a little bit. So we are out of the query complexity world now. Now everything is time and space complexity. Okay? So those complexity class, basically no query. But anyway, so first, quantum query class. So, not quantum query, sorry. Quantum complexity class that people think most about. Most famous is BQP. So it's basically a quantum version of P. Okay? And yeah, so that at a very high level, these class are the questions that can be efficiently solved by a quantum computer. Okay? And so the full name of this is bounded error quantum polynomial time. So it's P, polynomial time is same as the classical P. But so Q is obviously quantum, but we want B because we want bounded error. Okay? Bounded error means that, so we are saying decision, right? So decision problem, we need a success probability to be like at least 2/3, and at most 1/3 for yes instance and no instance. Okay? So there is a constant depth. Okay? Because so digression a little bit, because if you allow like arbitrary small error, right? So like 1/2 plus epsilon and 1/2 minus epsilon with like exponential small epsilon, then your algorithm can be much easier. Anyway, that's a digression. We are in a more sensible model where we have constant gap between our yes instance and no instance. And as we said, this is a complexity class or the class of problems that can be efficiently solved by a quantum computer. And if we go into details, then this is decision problems. Okay. Decision problems. Because we talk about yes instance and no instance. And it's an analog to P. Actually more like the classical randomized version. So there is also BPP, which is a boundary error and probabilistic polynomial time. Yeah. So the classical randomized algorithms. And just like P, people will use base notation about BQP. So people will say BQP machine to mean a quantum computer are wrong on polynomial time. Wrong, but it's actually a mistake because BQP is used to describe problems. People do that, so don't be too surprised when you see people say BQP machine and try to avoid saying that yourself. Okay, so that's BQP, and so in terms of quantum computer. Quantum computation, the first people think about is what's the relation between NP and BQP. So BQP are things we can efficiently do in a quantum computer, and NP problems are obviously very useful. It's useful in all kinds of practical problems. So I want to see whether quantum computers can solve NP problem or not. Well, so what do we know or what do we feel? And what do we feel is kind of, we think BQP and NP are kind of incomparable. So there is some instance that make you think NP might be inside BQP. That is this factoring problem that we spent quite a few time talking about. Right? So we know Shor's algorithm can solve factoring very efficiently. And we kind of believe that factoring is not in P and it's obviously in NP. But also we don't quite believe factoring is in NP complete problem. For reasons, mostly because we cannot prove it's NP complete. So yeah. So we feel like because of this factoring, BQP is a bit more than P, but we are not quite confident that BQP includes NP complete problems. Okay. And also there are things seems to be BQP but not quite verifiable. I don't remember that on top of head, but yeah. But yeah. We also think BQP is not quite totally inside NP, mostly because we cannot prove it. You know, there's something wrong with BQP, then that doesn't necessarily give you a NP witness verifier things. So we think BQP and NP are quite incomparable. And we also have some reminder that the thing about NP and NP complete is there are things that are NP hard, and if you are NP hard, that means it's harder than everything in NP. And the intersection of NP hard and NP is NP complete. So everything that NP can be reduced to NP complete problems. Okay, so that's NP versus BQP. And I should write this longer. And anyway, so we have very easy this containment relation we can prove. So P is obviously inside BQP because you can run every polynomial time classical computation on a quantum computer. Just run everything with toughly. And so there is a polynomial time blow up, but we don't care. So it's possible. And also, you know, this is a bit less trivial proof, but you can prove that BQP is in this P-space class. And P-space class is the class that allow you to use polynomial space. Okay, to say here. And it's actually a huge class because this is the only constraint. Okay. So it says you use polynomial space, but you can use any time. Okay. So potentially you can use exponential time. And P space is huge, so you can prove that NP is inside P space, and BQP is also inside P space. Okay. So yeah, so this is kind of the biggest problem, biggest complexity class that are encircling everything. And here we also have another thing that we didn't talk about, that is QMA. And you can see that it also includes everything of those inside. And so what is QMA? Is like a quantum version of NP. Okay. And here we have a very short exclusion, but at a very high level, is a quantum version of NP, means that it's the class of problem that can be efficiently verifiable by a quantum computer. So remember, NP there is verifier V and witness W, right? For some input X. So if your input is X, then there's a verifier that doesn't depend on your input, but you can run W that depend on X, and the verifier will determine whether your input is yes. Or if the input is yes, your verifier will accept, etc. So now if you think about generalizing this thing to quantum computer, then obviously you want your verifier now is a quantum computer. And also there is something different. Also you want your witness to be a quantum state. Okay? So witness, remember, it should be not too long, otherwise your verifier cannot run. But anyway, so you have a polynomial size witness, and now this polynomial size witness also become quantum state. So we say this is size of X. So problems that can be efficiently verified by this pair of things, so a quantum verifier. So I should say quantum verifier to make it things. Verifier. Okay. And quant is psi X, then it's called QMA. And okay, so it's a quantum version of NP, but a little more sad story. So this QMA, when people started, they call it like I think called BQMP, but it's because they think quantum NP. But then people in more computer science background decide to change it to QMA because it's actually the quantum version of MA problem. Okay, and yeah. So why is the MA problem? Because there is some error you are doing quantum computer. And so in NP problem, there is no probability you are either get accepted or rejected. But for QMA, your verifier is a quantum computer. So there is actually like a probabilistic thing. You can accept with probability something and reject with some probability. And if you are thinking about a verifier system that's probabilistic, then classically that's called MA class instead of NP. So it's actually QMA instead of QMP. Yeah. That's some side note. Okay. So anyway, that's the end of this slide. Any question? Yeah, short complexity review. And we didn't say where is the QMA. And so QMA is here. And so just like NP is bigger than P, so QMA, well, we don't really know it's bigger than BQP because proving separation is hard, but we know PQP is inside QMA. And also because QMA has this verifier structure, so it also contains NP. And with some work, you can also show QMA is still in P space. Okay. So the complexity class picture we think about is like this. Okay. Question?
So Q&A is also running the polynomial type, or
What do you mean? I mean, if you want to solve the QMA problem, it probably take exponential time. But its verifier can be run in polynomial time, just like in NP. So there is a quantum polynomial time verifier. So the verifier needs polynomial time, but it also needs to be a quantum computer. Okay. So quantum algorithm. Okay. So okay. So let's change to next slide. And let's talk a little more about Govern algorithm. Okay. So we spent quite a bit of time talking about this weird issue of the number of mark items in Govern's algorithm. Okay. So we say Govern algorithm, if there are n mark items, then you need all the square root n over m steps. Okay. And there is order over n items. But there are issues of whether this m is known or not, right? Because we say the success probability of the Govern algorithm is this sinusoidal, it goes up, down. And so the first big is this square root n over m, but if you don't know the n, then you can overshoot. Etc. Okay, so that's one problem. And the other problem is that when you run Goff's algorithm, you may not hit, even if you know n, you may not hit these mark items superposition exactly, and there will be some error here. Okay. And usually using constant error is okay, but let's give some motivation. But when you run this AND/OR tree, you find out that you really want no error. If there is no error, then things become much easier. Then you don't get this weird log n vector or the precision problem you want. Okay, so sometimes you want zero error algorithm. That would be much more useful. And okay, so there are two problems. So there are two problems, and then we can draw this 2x2 table of quantifier we want to add on our Govern algorithm. So first is there m known and known or unknown. Okay, and the second is you only want constant error or you want zero error. Okay, and the result is this table. Okay, so I guess the first three blocks are kind of not surprising. So if you have one constant error and m is known, then you can do order square root n over n. So this is just doing what we do in a textbook. And there are three other things. So if you don't know m but only one constant error, then you can still do order square root n over n. And otherwise, if you know m but want zero error, you can also do it. And but there is a surprising thing where if m is unknown and you want zero error, then you get no Govern speed up. You need omega n over m queries. Okay? That's basically what you need for. I guess it's not quite right because you want zero error. Okay, but anyway, there is this overbound. Although it might still have speed up over classical algorithm. Because, okay, yeah. Anyway, so those 4 results. The first one, as we said, is the textbook over. You just run a rotation up to somewhere close to this beta axis, and you will get a constant error, and you require square root and over n queries. Okay, and the second one, we kind of spend a lot of time talking about it, but but getting a not quite satisfying result. And anyway, if you doesn't know m, but you only want constant error, and so easy way to do this is you binary search through m. And we say that the extra number of query you need to do is like a geometric series, so it converges to just a constant vector, and you can do it. And otherwise, you can do quantum counting. But the textbook quantum counting is a bit weird because it requires you know m. So now that's the logical loop. So that's annoying. So you actually need a smarter quantum counting to get this order square root and over m. And yeah. And in the end, you need to do something similar to binary search. Okay, so that's that. And number 3 is if you want 0 error and you know m, and we hand wave through this, saying that you can do this by reducing your rotate angle. Right. So this thing, we say if you are going to overshoot, then and you know exactly how much you are going to overshoot, then you can just reduce the angle you rotate accordingly, precisely. So you will hit here exactly. And the thing is at the later part of this note. But I'm not sure we will talk about it. It's not too interesting. We'll see. We'll decide what we do next week. Okay, so that's that. And the fourth one, I guess it's something we cannot go into detail. But so we'll just say the result here is lower bounded once again by polynomial method. Okay. So yeah, there is this interesting table here, and we have a bit surprising result here, where if you want unknown m and 0 error, then you don't get this square root and speed up, but it seems like you still get 1 over n speed up, right? It's a bit weird. Okay, any question? These are basically reciting known results. Huh?
Exists any error correction method or
Error correction method? What do you mean? I mean, you can always do amplification, right? So if you want like a delta error, then you can just let's see, you are doing search, so search or decision, Let's say if you are doing decision. Oh no, we're doing search, but I think that's the same. So if you do like standard application, just you do things many times classically, then you want delta error, then you usually need like log 1 over delta vector to the number of times you need to run. So yeah, so you want to call from constant to delta error, then you only need to run this much. But this is particularly annoying because you want zero error, then you need to do something else. Because even if you do like a majority voting kind of thing, you always have some probability to get a very small error. So you will need to work extra hard to get this zero error here. So maybe we'll still do this next week. Okay. And okay. And now we talk about another modification to Grover's algorithm, kind of self-promoting, is that instead of finding whatever mark item, you can find the first mark item. Okay. So once again, let's say our truth table, our small f is here, and we can have f0, f1, f2, f3, etc. And you can think about there is an ordering, right? So we want to find the first mark item here, so this one here. Okay. And that's possible, and it's actually faster than kind of faster than doing total Grover search. Well, I guess not really. If you have a random distribution. But anyway, there is a modified version of Grover search, such that if you want to find the first mark item, and let's say the location of this mark item is D, then you only need order square root D 10 step. So just something about why this is not really that much faster. So say if you have m items, then D will be about n over m, right? So square root D is about square root n over m, and so that's what you expect. Okay. And yeah, so that's another homework. So you combine the minimum finding algorithm and the binary search, then you can do this order square root D algorithm to find the first mark item. Okay. And that is useful somewhere, at least in one of my paper. Okay. Any question? Otherwise, we have 10 minutes. I think it's about perfect time to talk through this amplitude amplification. So yeah, this is quite useful subroutine and the first step to do quantum work. And anyway, it's a generalization of Grover search. So the setting is like we set this up like Grover search. So we are still thinking, how do I say? So I guess well, let's run through this first. So we have this oracle function that you still want to find a mark item. Okay? So we still have this small f that has input 1 to n. Okay, so input 1 to n, and so f of x can be 0 to 1, and we want to find a marked item. So some x such that f of x equal to 1. Okay. But okay, so if you just have this, then you do Grover search. But now there are really two functions. So there is another function a here, this function a, and it lets you do something smarter than picking a random function. Okay. So there is this extra algorithm a that find a mark item with probability p, and so for this A to be useful, you want P to be better than random guessing, so P is something bigger than 1 over n. Okay. So, okay, let's say this in terms of Gover search. So we phrase this like enhanced Grover search. So we want to solve this search problem, but instead of just this checking oracle, you also already have some kind of smarter algorithm that do solve this problem to some degree. Okay. So you have this algorithm that find a mark item with probability better than totally random search, and with some cost, hopefully being efficient. And anyway, with this extra A possible, how fast can you find a mark item in f of x? And so if it is efficient, let's say this costs like a one-time step to do, then how many of those A you need to use to find the mark item? So classically, you cannot do things too smart. So you just keep running A, and each time you have probability P to find the mark item, then so you need about 1 over P times. Just keep doing A, and they give you a random item, and you run 1 over P times. Then you will have a constant probability to find the mark item. Okay? And but quantally, you can actually run a Grover around A, and you only need to query the quantum version of A, or the 1 over square root of P times to find the mark item. Okay? So yeah, so that's a generalization of Grover. You can Grover over this, checking these results from A. Okay? So that's quite interesting. And the other algorithm is called amplitude amplification. You will see, because it's kind of like we amplify the amplitude of the output of this algorithm A to have high overlap with mark item. Okay. And the algorithm requires you to call A, so basically run A. And but also we claim that we need to run this A inverse. So this inverse function of A as a quantum unitary. And we justify this by saying that if this A is not given you as a black box, so if you are given A as a quantum circuit, then you can just reverse every gate, then that will give you this A minus 1. That should be possible. And also, you also need to run a few of your original Grover oracle to check your answer. Okay. Anyway, so assume all those require like order 1 time, then the total algorithm only need to run order 1 over square root of P, and the square root is the square root speed up, just like Grover algorithm. And okay, about 5 minutes, so it's about time. And the algorithm like this. Okay, so it's not too hard. So you start with run your algorithm A basically. So you run your algorithm A on the O0 state, and it should give you something, and this something has the 1 P probability of being success. Okay? Right? Because that's the promise of a success. So that means that when you measure this in computational basis, then it has a 1 over P overlap to mark item states. And so you start with this, then you do steps that looks very like Grover's algorithm. You do 2 reflection. Oh, okay. Okay, so one thing is we also assume this P is known. to make things easier, because the P is like P, you are going to see P is like M over N. Kind of. We'll see that later. Anyway, so we'll do this repeated two reflection. So first reflection, just like in global algorithm, you want to reflect with your OF, so just your Oracle code to check whether item is marked or not. And the second reflection is this weird reflection. So you on computer A, then you do reflection around the starting O0 state, then you compute A back. Okay. And then we're going to say that this is not a reflection. It's actually a reflection around U. Okay. And so you do those order 1 over square root P times, then you measure a computational basis, and that should give you a mark item. Okay. And the proof is that this is like Grover's algorithm. So you look at this two-dimensional space with a beta that's equals to position of mark item, and if the U is a state that your algorithm A produce. Okay. And then this is alpha, is something orthogonal here. Anyway, so let's say this theta, angle is theta. And your algorithm will do two reflection, one reflection. Oh, what happened? Okay. Yeah. So one reflection is around this alpha, this OF we have been talking. Okay. Yeah. So one reflection is around this alpha, and another reflection is around. Wait. Reflection here, so your two reflection will rotate your angle by 2 theta, and your whole state will rotate this way, and you will end up getting somewhere close to beta. Okay, so first reflection we already see in Grover's algorithm, so let's skip that. And the only thing we need to prove is that this weird gate A minus 1 and the reflection on 0A is also a reflection on U, and we can just do the calculation here. So if you multiply all everything, and A0 is U, and A minus 1 U, now remember A is a unitary, so A minus 1 is A dagger. Okay. So this is actually A dagger 0, so that should be U bra. So this term become 2UK the U bra, and obviously A times identity times A minus 1, that's just A times A minus 1 equals the identity. Okay. So this is 2 times the projection on U and minus 1, and that's a reflection through U. Okay. And so you see that you are doing two reflections, and so now you do apply the Grover logic, and you should arrive here in 1 over theta times. And now the only question left is what is this theta here? And we can let theta is related to P in this way. So if you think about the inner product between this U vector and the beta vector square, and so in the picture that should be sin square theta. Okay. And that should also be the success probability of your algorithm A, because we know A has success probability P. So we know U has it. So we didn't define this rigorously, but high level idea is we measure A0 equal to U in contour basis. Then it has a probability P to be a mark item, so this should be also P. And anyway, from this relationship, we get that So we also approximate, so assume P is small, so we also approximate sin theta with theta. Then we get theta is about 1 over square root P. And we need order 1 over theta steps. So that's order 1 over square root P steps to get the Mach item. And we can come back to think Grover algorithm as amplitude amplification algorithm with A equal to this headma to the N. Okay? And if you think about this algorithm, it's basically picking a random item. And so the P will be M over N. Okay. So that's for today. And next Monday is a holiday, right? So we have no class. And next Thursday, I'm thinking we can. Next Thursday is already final. So I would say that don't have class on final, and we will teach something on next Thursday, maybe ending this slide. And we'll also have a final review on next Thursday. Okay? And the final week we will just don't have class. Okay. Then that's it. And see you next Thursday.